It's a pleasure to introduce the next speaker, Nathan Pagliaroli, who will speak on the critical behavior of ensembles of fuzzy spectral triples.
Yeah.
Again.
Thank you very much. Thank you for having me. So I'm really glad Luke went before me because that will save me a lot of time with background introductions to these objects. But basically, this is basically we're looking at the similar models to Luke, but we're looking at their critical behavior and also their interpretation in terms of their map interpretation. So this is based on joint work with Hamid Assam and Mizuka Kali. Okay, so just a bit of background. Luke touched on this before, but usually when you construct a theory of quantum gravity, the idea is to make sense of a partition function that sums or integrates over manifolds. Also, you usually have some matter fields involved, but what is meant by this is not clear because such an integral is wildly undefined, and there are a few different approaches, but generally you sum over geometric degrees of freedom, so usually over possible metrics over some class of metrics. But in our work, we consider integrals over spectral triples instead of manifolds. So in 2015, John Barrett proposed constructing a Euclidean theory of quantum gravity by integrating over some possible moduli space of all possible Dirac operators for a fixed algebra and Hilbert space. And the idea is that in NCG, as many of you probably know, Dirac operator takes the place of a metric in some sense. So the idea is instead of integrating over metrics, we integrate over some class of Dirac operators. But these integrals are still wildly undefined. To make sense of them, John Barrett considered integrals over certain natural, real, finite spectral triples. So we have a fixed algebra and a fixed Hilbert space, which are algebras of matrices, and we have some matrix Dirac operator D. So this Dirac operator is some matrix that acts on the Hilbert space, or spinor space, and the type PQ that we'll keep referring to. So Luke was dealing with 0, 1 fuzzy spaces refers to the signature of the Clifford module B. And as Luke mentioned also, John Barrett found a way to classify all such Dirac operators on these fuzzy geometries. And it turns out that they can be written as some sum of anti-commutators and commutators of skew Hermitian, traceless skew Hermitian, and Hermitian matrices with some tensor to some products of gamma matrices that depend on the Clifford module. For example, so type 1, 0 is D is equal to H, the commutator of H. For 0, 1, as we saw with Luke, it was the anti-commutator. With Luke, it was the commutator. Type 0, 2, we have some Pauli matrices tensored with commutator of 2 matrix variables, which are Hermitian. We're mostly just interested in type P0 because the map interpretation for Hermitian matrices is much simpler than for traceless skew Hermitian matrices. So what Barrett and Glaser proposed in a follow-up paper was that we can add a probability distribution on D for fixed algebra and a fixed Hilbert space of fuzzy geometries or fuzzy spaces, and we get an ensemble of Dirac operators. So usually it's of this form with some polynomial function S of D, although any function could be considered in theory, where dd is defined as the product Lebesgue measure on some Cartesian product of those skew Hermitian, traceless skew Hermitian, and Hermitian matrices that we saw in the previous slide, which depends on your choice of PQ. And we refer to a fuzzy geometry equipped with a probability distribution on the entries of D as a Dirac ensemble. So, for example, very similar to Luke's model, we have a quartic, but now type 1, 0 ensemble, where T2 and T4 are coupling constants. And in this case, dd just becomes the Lebesgue measure on the space of n by n Hermitian matrices. But we can also write this in terms of our Hermitian matrix H. And as Luke pointed out, we get product of trace terms, which complicate things. But this is still widely the most simple, interesting model, because it has examples of phase transitions like Luke mentioned. Well, if you just looked at a Gaussian term, you don't get any interesting behavior. But in general, Dirac ensembles with polynomial potentials are bitracial, so they have products of two traces in their exponential, but they're also multi-matrix. So there's lots of words and matrix variables that we're taking trace of, and this usually the usual techniques in random matrix theory that are used to study these models are not applicable, at least immediately. But one way that we sort of get around this is we consider their Feynman diagrams, and we consider perturbative expansion. And it turns out actually often is the case with matrix integrals is if you understand the leading order term of the perturbative expansion of the integral, you can sometimes recover the convergent behavior of the corresponding convergent integral. So the rough idea goes as this. When you perturbatively expand our integral, so you drop the potential term and series expand it, swap the order of integration and summation, you get a sum over Feynman diagrams. And in the case of matrix models, Feynman diagrams are surfaces embedded with graphs. They're called maps, and they can be thought of as discretized Riemann surfaces. And another common phenomenon in matrix models is that if you tweak the coupling constants to some critical value, the number of polygons or faces that make up these maps, so these embeddings, goes to infinity. And so the idea is that in some sense you'd be counting Riemann surfaces. This idea can be made a little more precise. But what we found in our recent work was that these critical points exist in certain Dirac ensembles. And we were able to show that these models have the same critical exponents and the asymptotics of partition functions as certain minimal models from 2D conformal field theory. So I'll go into more detail about that. So suppose we have our partition function z, so that our matrix integral. We take its log so that instead of just summing over these graph embeddings, these maps, we're now summing over connected maps, which is a lot easier to count. And we get an expansion. We get an expansion in terms of genus. So this is completely analogous to loop expansion in quantum field theory, where you can organize your contributions to your partition function or log of your partition function by number of loops you have in your graphs. Here it's the number of handles instead. And each particular FG, so even though our original integral may not be convergent, well, it is definitely not convergent, our FGs might actually be convergent for some range of our coupling constants. So these FGs are the generating functions of these Feynman diagrams, and that are called maps. So here we have a sum over TV, where T is some redundant coupling constant that keeps track. So this keeps track of the number of vertices in your map. W is some Feynman weight, and the automorphism factor is the number of automorphisms of the maps that weights the sum. And in particular, these usually maps are glued from just polygons, but when you have bitracial matrix models like these, you actually get different contributions from like two cells with the topology of a cylinder, for example. And in multi-matrix models, you get colored faces and colored edges, which make the gluing even more complicated. But in general, this FG is remarkably an algebraic or a logarithmic function. In fact, it's almost always algebraic of its coupling constants. And they can be computed from the general correlation functions, that's what W0Ks are, using a process known as topological recursion. So there's a recursive process where if I know the first two leading order contributions to my correlation functions, I can compute all the others up to any given order, and you can actually recover the expansion of the partition function from those correlation functions. So for example, for the quartic type 1,0 Dirac ensemble that we saw from before, one can show that each of these FGs, we can compute them, but we're also interested in the critical behavior as the number of faces goes to infinity. And the singular part of it, so it's asymptotic expansion, near the critical point or curve, is of the following form. You have some constant, you have some constant CG, you have an expansion around your critical point, if we just have everything in simplified case, and you have some critical exponent here. And this is true for all g's except when g is equal to 1, in which case our singularity is logarithmic, and we have some constant in front. So these cg's are constants in terms of the coupling constants. And we can compute them explicitly, but this is roughly what they look like. And what you can do is you define a new formal series. So this may seem out of left field, but there is motivation for this that I don't have time to get into. You define a new formal series of these constants in front. This is sort of valuable information. And it turns out that this generating function that we construct with those CGs satisfies the Pagliaroli 1 differential equation to all orders. So remarkably, and this is actually the exact same behavior that you see in a minimal model from conformal field theory. They predict the same thing. They have the same critical exponents and the same asymptotics, and they also, you can construct this generating function that satisfies Pagliaroli 1. And this is sort of a remarkable fact that it happens in Dirac ensembles, but this is well known to work in general into simpler matrix ensembles since the 90s. And in general, different matrix models are associated to different so-called minimal models, and their FGs satisfy some other differential equation, depending on what those critical exponents are. So, for example, these critical exponents, so P over Q, correspond to two integers that represent the conformal group in 2 dimensions and have a minimal model. So 3, 2, which was the one in this case, is called pure gravity, and it corresponds to cubic and quartic type 1 zero Dirac ensembles. 5, 2 is called the Yang edge singularity, and it corresponds to the hexic model that we studied. The general question, though, is, well, in general, we know single trace matrix models correspond to type P2 minimal models, and more general PQ can be found in multi-matrix models. But for Dirac ensembles, we don't know beyond just these 3 examples yet. We conjecture that a similar pattern for single trace occurs, but we have to prove it, and we have some ideas about that, but that's an ongoing work, and whether they even appear. Now, more recently, we've studied the 2 matrix models, so type 2, 0, 1, 1, and 0, 2 quartic Dirac ensembles. And so it's just a quartic potential like before. But now, if we write our action in terms of 2 matrix variables A and B, then it looks like this. So this is quite ugly. It's extremely complicated. I'm writing all 3 potentials at once because the only difference between them is some signs, these epsilon 1s and 2s, which you can find in this chart. So type 2, 0, for example, all the epsilon 1s and 2s are just 1, and it's different for each one of them. And these signs correspond to the KO dimension. But this is a really difficult integral to solve because you lack unitary invariance in your model, which is usually one of the ways that you solve matrix models is by of using its unitary invariance, and it's also multi-trace, so it's quite challenging. But we recently found a solution. So we were able to currently compute any moment recursively from the second moment, and we found an explicit expression for the second moment of our ensemble. And from that, you can actually compute the leading order term. So this is like our F0, so of the free energy, so it's of the log Z. And it looks like this. So large and limit of the free energy, the log of the partition function, can be expressed explicitly in terms of the coupling constants like this, which is actually remarkably much simpler than for the type 1, 0. And the reason is because graphically as you're counting less maps, because there's more constrictions on the types of maps or the Feynman diagrams that you're counting. But we have this beautiful explicit expression. And what you can see from this expression is that it's not going to be analytic at where t2 squared is equal to minus 8t4. Some of its derivatives will blow up at that point. And so that's our critical point. Like in the type 2, 0, I didn't say what the critical point was, and I didn't show the whole function, but it's basically the same idea. You find where your map generating functions blow up, and in this case, it's along that curve. And interesting, so the critical exponent, the one of main interest, is called the spring susceptibility exponent. And for the type 1, 0 quartic Dirac ensemble, it was minus 1/2, which is very typical of matrix models. But for this one, it's 1/2. And this is in some multi-matrix models, I believe this is the case. But it's also a very common string susceptibility exponent for tensor models. So it's interesting. And I do believe that some of these integrals may have an interpretation as tensor models as well, but this is kind of ongoing research. And these two different string susceptibility exponents hint at different continuum limits, but this also requires further investigation. There's different random metric spaces that you can talk about convergence of these maps to, but this is ongoing work. So that's everything. Thank you.